so 7.1 is titled Integration by Parts. Now let's see if we can justify where integration by parts comes from. So integration by parts is going to be the inverse or the undoing of the product rule. So if we have two functions, u and v, and we take their derivative, d dx of u times v by the product rule is u v prime plus u prime v. That's just our product rule. So then the idea is, if we then integrate both sides of this equation, so we take the antiderivative of this entire equation, we can integrate each term separately. In the first term, the integral and the derivative by the fundamental theorem of calculus part 1 undo each other. And we're left with u times v is equal to the integral of u v prime plus the integral of u prime v. So we could then minus this integral from both sides of the equation. So we subtract the integral of u prime v from both sides, so those reduce out, and that leaves us with the integral of u v prime is equal to u times v minus the integral, and I'm going to write the integrand in the other order, vu prime. So it's traditional to use the d notation instead of the primes. So finally we get the formula for integration by parts as u dv. So the integral of u dv is equal to uv minus the integral of v du. So basically this formula right here is what we're going to use every time we need to do integration by parts. And we're going to talk about how we can use it and what we're going to need to calculate. So the big idea is we want to calculate the integral of v du, which would mean we have to know how to integrate du when it comes to using this. So the big idea is we're trading one integral that we don't know how to do for a different integral. And we always want to trade up. You don't want to trade for something worse than what you started with. And we'll see that that can happen. So our goal is to get something that we know how to do as opposed to getting back again something we don't know how to do, right? So that's kind of our big meta plan. So when using integration by parts, we pick dv and u. So dv, we must know how to integrate. And u, we must know how to differentiate. So we're going to be picking each of these and then using our formula above. So we pick u and we pick dv, and then we're going to put all of them into our formula and calculate. So let's start with example number 1. So we wish to find the integral of x e to the 3x dx. So we are going to pick, and I always like to organize these things as a table. So we're going to pick, or I'm going to pick, u is equal to x, because I know how to take the derivative of x, and I'm going to pick dv to be e to the 3x. So then, after we've picked u and we picked dv, we need to calculate the other two parts of the formula, which are du and v. So we calculate du by taking the derivative of u. So if u equals x, what does du equal? Well, what's the derivative of x? 1 dx, or dx. And then we also have to calculate v. So what is the antiderivative of e to the 3x? Yeah, so e to the 3x divided by 3. So now we can use our formula to calculate our integral. So the integral of x e to the 3x is equal to u times v minus the integral of v du. So filling in the parts that we just calculated, we have u times v is going to be x times e to the 3x over 3 minus the integral of v du. And we're going to have e to the 3x over 3 dx. So notice, after using the formula for integration by parts, all we've done is created a different problem from the original that hopefully we can solve. Our original integral was x e to the 3x dx. We know that that integral is equal to x times e to the 3x over 3 minus the integral e to the 3x over 3 dx, right? So we traded our first integral for a second integral. And we're hoping now that we can figure out how to integrate this one. And in this case, we can, because we've actually already done that integral. So cleaning everything up a little bit, we have x e to the 3x is equal to x e to the 3x over 3. Pulling our 1/3 out of our integral, because it's just a constant, we have the integral of e to the 3x dx. And in fact, we did that up here. What's the integral of e to the 3x? E to the 3x over 3, right? So we finally get x e to the 3x over 3 minus 1/3 times e to the 3x over 3 again, plus our constant, and we get x e to the 3x. I lost my dx that whole time, didn't I? Dx is equal to x e to the 3x over 3 minus 1/9 e to the 3x plus c. So that would be our antiderivative of x e to the 3x. And we could check it by taking the derivative to make sure we get back the original function, which we would. So when we're doing integration by parts, our strategy is we have to pick u and we have to pick dv. We take the derivative of u and we take the integral of dv to get du and v, and then we plug into the formula and try to integrate the result of plugging into that formula. I had also mentioned that we won't always get something better when we try the integration by parts formula. So I'm going to redo example 1, but in a method that's not going to make the problem easier. So what if we reversed our choice of u and dv? So what if I pick u to be e to the 3x, and I pick dv to be x? Well, I can still integrate and differentiate both of these, right? So then du would be 3e to the 3x dx, and the antiderivative of x is x squared over 2. So if I plug into the integration by parts formula, I get u times v, so x squared over 2 times e to the 3x minus the integral of v du. So I'm going to get x squared over 2 times 3e to the 3x dx. So I clean that up a little bit, so we get x squared e to the 3x over 2 minus 3 over 2, the integral of x squared e to the 3x dx. And now I look at this, do I know how to do the integral of x squared e to the 3x? I don't, and in fact, it looks more complicated than the integral I started with. The integral I started with was almost exactly like this, except for it had a linear function times e. Now I have a quadratic function times e. And in fact, it's gotten more complicated. So if something like this happens when you're doing integration by parts, you trade your integral for something that seems more complicated than what you started with, a couple of things could be wrong. Integration by parts might not be the right method, or maybe you should try picking a different u and a different dv, right? So in this case, what we pick is important. So this is more complicated. So try a different choice. And as we did the first time, we actually got the answer by picking them the other way around. So while we do have a lot of latitude in choosing different things, we do have to be a little bit careful, because if we pick the wrong things, our formula for integration by parts will get messier instead of nicer. We're going to pick our u to be t. We're going to pick dv to be the sine of 2t dt. So the derivative of u is du, and derivative of t is dt. We integrate dv and we get v. The antiderivative of sine is negative cosine, but then it's not sine t, it's sine of 2t. So we have to divide by 2. And we get then, using our formula for integration by parts, the integral of t sine 2t dt is equal to u times v, so negative t times cosine 2t over 2 minus the integral of v du. So minus the integral of negative cosine 2t over 2 dt. So simplifying, we have a minus minus makes it a plus, and we can pull the 1/2 out of our integral. So we get 1/2 times the integral of cosine 2t dt. So we can directly find the antiderivative of that in a similar way that we did above. And the antiderivative of cosine is going to be sine, so we're going to get sine 2t, but we divide it by 2 again, plus our arbitrary constant, giving us negative t cosine 2t over 2, plus sine 2t all over 4, plus our arbitrary constant. And that would be our antiderivative of t sine 2t. So once again, we pick u, we pick dv, calculate du and v, plug into our formula, and we integrate, hoping that we get an integral when we're done that we do know how to integrate. All right. So you might be thinking, well, in these first couple of examples, it seems like for u, each time we picked the polynomial. And often that's not a bad choice. So one thing that makes integration by parts, or integration in general, more difficult than derivatives is we don't have a definitive rule for every type of integral you run into. But we do have some suggestions. So what I'm going to write down is a general rule of thumb to help you pick u, but there are exceptions to it. So it's not a rule so much as it's a place to start. And if that doesn't work, try picking a different u. Sometimes you have to pick more than one until you will find the correct one that will get you what you want. So there's the mnemonic that will help, maybe, LIATE, and each of these stand for something. So L is for logarithm, I is for inverse trig, A is for algebraic, T is for trig, and E is for exponential. This is a suggestion for the order to pick u. And we should go from here, from left to right. So basically, this suggestion says if there's a logarithm, try that for u. If there's not a logarithm, try an inverse trig. If there's not an inverse trig, algebraic is like polynomials or rational functions, like what we saw in the last two. And then after that is trig functions and exponential functions. So in each of the last two examples, we picked algebraic. The example I did had an exponential, which is what we ended up picking for dv. And the example you did had a trig function, which we ended up picking for dv, and we picked u to be the algebraic or the polynomial in both. So this rule of thumb worked for these first two examples. So 2 examples does not a proof make, but it's not a bad place to start if you're not sure what to pick. All right, so let's keep working on some examples. So our next example, example 2, is the integral of t cubed, the natural logarithm of the square root of t. So according to our suggestion, what should we pick for u? A logarithm. Okay. So before we do that, though, we want to use some properties of logarithms and algebra to help simplify this up a bit. So let's use algebra. So the 2 things we're going to need to do is our fractional exponent plus log properties. So our fractional exponent is if we have the square root of x, that is the same as x raised to the 1/2 power. We have our log property that we want to use, which is if we have the logarithm base a, or logarithm of a raised to the b, this is the same as b times the logarithm of a. That's our power rule for logarithms, which states if we have an exponent on the argument of a logarithm, that is the same as the product of the exponent and the logarithm. So using these two properties, we get that the integral of t cubed, the natural log of the square root of t dt, would be the same as the integral of t cubed times the natural logarithm of t to the 1/2 dt, and then bringing the 1/2 out in front, we can pull the constant just right out of the integral. And that basically eliminates the square root from the problem, right? So we rewrote our logarithm terms of fractional exponents, and then we pulled that 1/2 exponent down in front, but since it's a constant, we just pulled it right on out of the whole integral. So now we're dealing with just the integral of t cubed times the natural log of t. And as we talked about at the beginning, our suggestion then becomes that we pick u to be the natural logarithm of t. So we pick u to be ln t, then everything that's left becomes dv, so dv is t cubed. So now we calculate du. The derivative of the natural logarithm of t is going to be 1 over t dt. And the integral of t cubed is going to be t to the 4th divided by 4. So 1/2 times the integral of t cubed natural log of t dt is equal to, well, we have the 1/2 that is out in front of everything, and then we have u times v, so we're going to get the natural log of t times t to the 4th all over 4 minus the integral of v du. And for that, we have the integral of t to the 4th over 4 times 1 over t dt. So let's distribute our 1/2 in and simplify a little bit. So we get t to the 4th times the natural log of t. 2 times 4 gives us 8 minus 1/2. But distributing that in, we also have a 4. We get minus 1/8. The integral. And then we have t to the 4th in the numerator, but a t in the denominator, so that reduces to t cubed dt. So t to the 4th divided by t is t cubed. So now we want to calculate this integral. So we get t to the 4th ln t over 8 minus 1/8. And the antiderivative of t cubed, oh, we've already done that. It is t to the 4th over 4 plus a constant. So finally, at the very end, we end up with t to the 4th natural logarithm of t over 8 minus t to the 4th over 32 plus a constant. So when we look back, when we picked u to be the natural logarithm of t, especially when our other term was a polynomial, things work out really nicely because the derivative is 1 over t, and then the polynomial pretty much reduces out that derivative and left us with a nice simple integral to work with, right? Because we can integrate polynomials all day. We love that rule. Add 1 to the exponent and divide by it. If all integrals were polynomials, we'd be integral ninjas. So, All right. So now your turn to take a look at the. All right, so let's go ahead and see what we get. So if we pick u to be the natural log of t, and we pick dv to be dt, then the antiderivative of dv is t, and the derivative of ln t is 1 over t dt. So we get that the integral of the natural logarithm of t dt is u times v, so t ln t, minus the integral of v du. So t times 1 over t dt, and our t's reduce out, and that leaves us with t ln t minus the integral of dt. So that's t ln t minus t plus constant, right? So that's our antiderivative of the natural logarithm of t. And when we're finding antiderivatives or indefinite integrals, how can you always check that your answer is correct? Well, what is the indefinite integral the inverse of? The derivative, right? So if we differentiate what we just got, we should get back the integrand of what we started with. So let's check. So if we take the derivative d dt of t ln t minus t plus a constant, well, to take the derivative of t natural log t, what rule do we need to use? Well, that's going to be product rule, right? So that would be f is t and g is ln t. So then f prime is 1 and g prime is 1 over t. So our product rule is f g prime. So we're going to get t times 1 over t plus 1 times the natural log of t. That's our product rule. What's the derivative of negative t is 1, and the derivative of a constant is 0. So we get 1 plus the natural log of t minus 1. And those reduce out as we would hope. And indeed, we get back to the very thing we started with, which was natural log of t. So remember, the fundamental theorem of calculus part 1 tells us that integrals and derivatives are inverses of each other. So if we integrate something, the indefinite integral is the antiderivative, just another way of saying it. So if we take its derivative, we should get back what we started with every single time. So we can always check that we did the integral correct by taking the derivative of our answer and making sure we get back what we started with, right? So derivatives and integrals undo each other just like addition and subtraction and multiplication and division. So to undo an integral, we use a derivative. To undo a derivative, we use an integral. All right. So now we're going to look at a problem that will help us generate a formula which can be helpful. So there's also a technique in this problem that we're going to use that's going to seem a little strange at first. We hinted at it earlier, and we're going to use it again. So to go back to the very, very beginning, when we did integration by parts, I took the derivative of both sides, and then we integrated. And then in this line right here, what did I do? I subtracted an integral from both sides of the equation. Integration by parts gives us an equation. So as long as we balance that equation, we can add or subtract the same thing from both sides. We can also multiply and divide the same thing on both sides as long as it's not 0. So since it's an equation, we will be able to use all of our properties of equations as well. We're going to use that to help us resolve this next integral. So looking at our integral, we have e to the ax times sine bx dx, where a and b are constants. All right, so let's pick our u and let's pick our dv. So we have u equals ea to the x, and we're going to pick dv is equal to the sine of bx. So then du is going to be a times e to the ax. And the antiderivative, well, the antiderivative of sine is negative cosine bx, but then we have to divide by b. So writing out our integration by parts, we have the integral of e a to the x sine bx dx is equal to u times v. That's going to be negative ea to the x cosine bx all over b minus the integral of v du. So we're going to have negative cosine bx over b times a e to the ax dx. So we have a minus minus, which is going to give us a plus, and then we have some constants inside of our integral that we can pull out. So that gives us the integral of e to the ax sine bx dx is equal to negative e to the ax cosine bx, so all that same stuff over b, plus I have an a in the numerator and a b in the denominator that are both constants. So a over b times the integral of e to the ax cosine bx dx. So after using integration by parts once, I'm not entirely sure that we've actually made any progress. What was the integral we started with? ea to the x sine bx. What integral did I trade that for? E to the ax times cosine bx. So I traded the one with sine for the one with cosine. Like I said, I'm not entirely sure I made any progress, but it's definitely not worse than what I started with, right? So, all right, let's keep going. Let's try again. So let's do integration by parts one more time. So this time, if we pick the same thing, well, almost the same thing, if we pick u to be e to the ax, and we pick dv, this time to be cosine bx dx, then du is a e to the ax dx, and v is going to be sine bx divided by b. So we integrate by parts again. Let's plug into our formula and see what happens. So we have the integral of e to the ax sine bx dx is equal to negative e to the ax cosine bx over b plus our a over b. And now we're plugging in our integration by parts formula again. So we have u times v, which is going to give us e to the ax sine bx over b. So that's our u times v minus the integral of v du. So we're going to get sine bx over b times a e to the ax dx. Close our parentheses. Okay. So let's clean a couple of things up once again. So I can take my a and my b and pull them out in front of my integral again, right? So then let's distribute that a, b back into our parentheses. So if we do so, we get the integral of e a to the x sine bx dx is equal to negative e to the ax cosine bx over b. Distributing that back in, we get plus a e to the ax sine bx divided by b squared minus a squared times b squared times the integral of sine, let's put the e in front. Let's do it, e to the ax sine bx dx. So now at this point, you're like, what the heck? We went full circle. What was the integral we started with? E to the ax times sine bx, right? Well, what's the integral we got back this time? E to the ax sine bx. Well, notice that these two things are the same. We're going to use that same technique that we did at the very beginning. We have an equation, right, with an equal sign. So we can add that integral to both sides of this equation. So I can add a squared over b squared, the integral e to the ax sine bx dx to both sides, plus a squared over b squared, the integral e to the ax sine bx dx. And when I do, on the right-hand side, they are equal but opposite, so they reduce out. And on the left-hand side, that leaves me with the integral of e to the ax sine bx dx plus a squared over b squared e to the ax sine bx dx equals negative e to the ax cosine bx over b plus a e to the ax sine bx all over b squared. So now we just need to finish solving for that integral. Well, we have a common factor of that integral that we can factor out, right? Because I have that in each of them. So if I factor out the integral e to the ax sine bx dx, that's going to leave behind 1 plus a squared over b squared times the integral e to the ax sine bx dx is equal to this, and in this piece over here, let's go ahead and just get a common denominator so we can combine these. So when we multiply the top and the bottom of the first one by b, and that gives us negative b e to the ax cosine bx plus a e to the ax sine bx all over b squared, right? So now we can do something similar to this piece right here, getting a common denominator. We would get our common denominator would be, let's not use red, would be b squared, right? So then that would leave me with a squared plus b squared over b squared times our integral e to the ax sine bx dx equals this. I'm going to rearrange it to put the positive term first and factor out anything that's common. So we can factor out an e to the ax and a b squared, so that gives us e to the ax over b squared, and then that leaves behind a sine bx minus b cosine bx. So finally, to finish up, we divide both sides by a squared plus b squared over b squared, and we divide by a squared plus b squared over b squared. And when we divide two fractions, it's the same as multiplying by the reciprocal. So after all of that, we get that the b squareds, if we multiplied by the reciprocal, would reduce out, and we're left with e to the ax times a sine bx minus b cosine bx all over a squared plus b squared. Holy guacamole, right? So the most important part of that entire thing was the technique that we used up here, where we added the same integral to both sides of an equation. So the key thing to remember here is that integration by parts gives us an equation. So if we need to move things from one side to the other to help us further our goals, by all means, we can use any algebra at our disposal. So this technique will come in handy at other points in our semester to help us resolve some integrals. So just for right now, keep that in mind, that technique will be helpful in solving certain integrals. So if you end up with something that looks the same on both sides of an integral, collect it up, right? Add them to both sides and solve for it. All right, so let's keep on going. Our next ones aren't quite as intense. As that last problem. Now you understand why it got its own page in the notes, right? So let's go ahead and do this one. So this is really similar to one we did at the very beginning. So we're going to pick u equals x, and we're going to pick dv equals e to the x. So the integral of dv is v is e to the x, and our derivative du is going to be dx. So we get that our integral is going to be u times v, so x e to the x minus the integral of v du. So e to the x dx. So we have x e to the x minus the integral of e to the x plus c. So our antiderivative of x e to the x is x e to the x minus e to the x plus c. All right, let's do example number 5, but let's do a little comparing and contrasting. So example 5 looks a lot like example 4, But the only difference is, instead of an x, I have an x squared. So we're going to try the same thing that we did on the previous one. We're going to pick u equals x squared, and we're going to pick dv equals e to the x. So then v is e to the x, and du is 2 times x dx. So we do our integration by parts. So we have u times v is x squared e to the x minus the integral of v du, which is going to be 2x e to the x dx. And we pull out our constant 2, and we have x squared e to the x minus 2 times the integral of x e to the x dx. And we're like, wait a minute. So when I did integration by parts, I started with a degree 2 polynomial, and what did I trade it for an integral of? A degree 1 polynomial. And as a matter of fact, that's the integral that we just did in example 4, right? So by 4, our answer is going to be, we have our x squared e to the x minus 2 times the answer we had up here, which is x e to the x minus e to the x plus our constant. So we clean that up, x squared e to the x minus 2x e to the x minus makes it plus 2 e to the x. Interesting. Very, very interesting. All right, example, well, not example because it's a U-try 3, aka example 6. I want you guys to do it, so what are we going to pick for our U this time? Yeah, we're going to pick U equals x cubed, and we're going to pick dv equals e to the x. So let's go ahead and resolve this integral. And dv to be e to the x dx. We get v is e to the x, and du is 3x squared dx. So we have u times v, which is going to be x cubed e to the x minus the integral of v du. Well, v is e to the x, and du is 3x squared dx. So we get 3x squared e to the x dx. Taking our constant out of our integral again, we get minus 3 times the integral of x squared e to the x dx. And fortunately for us, and hopefully you noticed, this was exactly example number 5, right? So then putting that in, we get x e to the x minus 3 times our answer from the previous one was x squared e to the x minus 2x e to the x plus 2 e to the x, and then plus a constant, right? So then if we distribute that minus 3 in, we get x e to the x, x cubed, my cube just disappeared, minus 3x squared e to the x, minus makes it plus, so 6x e to the x minus 6 e to the x plus c, right? So a couple of observations. If we didn't know example number 5 and have that answer already, we would have had to done integration by parts again, right? And then if we didn't know the answer to number 4, we would have had to do integration by parts again. A matter of fact, our integrand started with a degree 3 polynomial and an e. all told, we would have had to do integration by parts 3 times, which is the same as the power on our polynomial, right? So each time we did integration by parts, what happened? It reduced the degree of the polynomial by 1 because we took its derivative until we would finally get down to like what happened in our very first example, where our new integral didn't have a polynomial at all. It just had an e to the x in it, right? So we may have to do integration by parts more than 1 time in any given problem. There's also something interesting that we might want to take note of. So if I were to make an observation, if I call this function u, oops, and if I call this function dv, I might notice something interesting that happens down here. So x cubed is u, 3x squared is u prime, 6x is u double prime, and minus 6 is u triple prime, right? No primes, 1 prime, 2 prime, 3 prime, because the derivative of x cubed is 3x squared. The derivative of 3x squared is 6x, and the derivative of 6x is 6. And with our dv, we'll notice that this is the integral of dv. This one is the second integral of dv. This is the third integral of dv, and so forth, right? So we get a pattern that is happening here. Because essentially what we're doing when we do integration by parts is we're shifting the derivative from one function to another. But to keep it balanced, we have to do the opposite to the other term in the product. So if we're differentiating one, to balance it, we have to integrate the other. So we're transferring derivatives as we do this. So that's one way to visualize integration by parts. The one last thing that we'll notice is that the sign changes every other time. It goes plus, minus, because we have that uv minus the integral of v du. So each time you do integration by parts, it's flipping the sign of each of these. Turns out we can use this, because what is mathematics really? It's the study of patterns, right? We're looking for patterns in numbers and functions. So this gives rise to what is referred to as tabular integration. So theorem, tabular integration. If f of x is a polynomial and g is a function with antiderivatives that cycle, so something like e, sine, or cosine, so those are our 3 possible choices, then when we do the integral, we can recognize it in terms of that pattern. In the summation notation, it's not real apparent what's happening. So we'll organize it into this table below. So what it says is we put f and g in the table, where f is the function that we're going to take the derivatives of, and g is the function that we're integrating. So f is u, and g is dv. And we differentiate down the first column, and we integrate down the second column. We change the sign of every other term in the first column, and then we're going to multiply down the diagonals until we get to the 0 term, because 0 times anything is going to be 0, right? Because once the polynomial gets to 0, we can stop, because then there's going to be no more terms, because the 0 will knock all of that stuff out. So I know at first glance this table isn't terribly enlightening. So let's actually write an example out and see how we can apply it. So before we do that, if I were to look at my integral x to the 6th times cosine 2x, how many times would I have to use integration by parts if I wanted to integrate this? 6 times I would have to integrate by parts, plus one more integral at the end for the ones that's not by parts. So if you try to do this the long way, and there are ones like this in your homework, don't. You will be integrating for about 30 minutes. It's not worth it. Use the tabular integration method whenever you have a polynomial times sine, cosine, or e. So the way we set this up is we put our polynomial in the first column, and in the second column, we put our function that cycles. And we are going to take derivatives down the first column. So the derivative of x to the 6th is 6x to the 5th, 30x to the 4th, 150x cubed. Yeah, I can't multiply. That's 120. 120x cubed, 360x squared, 720x, 720, and then finally we get to 0, right? That's our derivatives of all of those things. Then we make every other one of these negative. So it goes positive, negative, positive, negative, positive, negative, positive, negative. And we knew we stopped when we got to 0. Now we're going to integrate down the second column. So the antiderivative of cosine is sine 2x over 2. The antiderivative of sine is negative cosine 2x over 4. The antiderivative of cosine is sine, so we get negative sine 2x over 8. The antiderivative of sine is negative cosine, so minus minus makes it positive. So cosine 2x over 16. The antiderivative of cosine is sine, so sine 2x over 32. And then the antiderivative of sine is negative cosine, so negative cosine 2x over 64. One more, and the antiderivative of cosine is sine, so we get the sine of 2x all over 128. So now, to finish, we connect all of the diagonals. And see, the reason we stop here is if I kept connecting the diagonals, I would have 0 times something, so we know we're done, right? So now our antiderivative is going to be x to the 6th times the sine of 2x over 2. And then I have a minus and a minus, so that's going to be a plus. So plus 6x to the 5th cosine 2x over 4 plus, nope, it's going to be negative because I have a positive times a negative this time gives me negative 30x to the 4th times sine 2x over 8. And then we get to our next one, a minus times a plus gives us another minus, so 120x cubed cosine 2x all over 16. We get to our next one, so 360x squared, so plus 360x squared sine 2x over 32. And then minus minus makes it plus, so 720x cosine 2x over 64 minus 720 sine 2x all over 128 plus our constant plus c. And that would be our antiderivative of that. Just be glad you didn't have to do integration by parts 6 times, plus one more integral, right? So the key idea with tabular integration is you put the polynomial in the first column, differentiate down that column, and then make the sign pattern go positive, negative, positive, negative, positive, negative, positive, negative. Integrate down the second column, and then multiply down the diagonals, and that will give you your antiderivative. It will save you a ton of time. I'm sorry, I owe you guys 2 minutes. I stole it from your life, so we'll stop here. So